Welcome to The Explainer. We're all about breaking down the big ideas that really shape our world. And today, we're digging into one single research paper. It sounds kind of dry, right? But this paper didn't just nudge AI forward, it completely changed the game.
So, you ever stop and wonder, how does something like ChatGPT actually get what you're saying? I mean, really understand the nuance, the context, the whole vibe of a sentence? Well, the answer, or at least the seed of the answer, is in this wild 2017 paper from a team at Google. Its title was Attention is All You Need, and they weren't kidding. They didn't just tweak the old ways of doing things. They basically threw the whole rulebook out the window.
All right, so to really get why this paper was such a big deal, we got to go back in time a little bit. We need to understand the problem they were up against. Because before 2017, AI for language was, well, it was stuck. It had hit a wall.
So the best models back then were called recurrent neural networks, or RNNs for short. And they worked a lot like how we read. One word at a time, sequentially. So to figure out the meaning of the last word in a sentence, it had to remember every single word that came before it. You can probably see the problem here, right? It was a massive bottleneck. Not only was it painfully slow, but the model had a terrible memory. By the time it got to the end of a long paragraph, it had pretty much forgotten what the beginning was all about.
And this, right here, this comparison nails the problem perfectly. The old way, the recurrent models, they were stuck in this one word at a time loop. It was the very definition of a bottleneck. And you couldn't just throw more computers at it to make it faster because the method itself was the problem. It was a dead end. AI was just fundamentally bad at connecting the dots in long, complex sentences.
So, this is where it gets really good. This whole situation, this roadblock, it set the stage for something totally different. A team at Google came along and asked a question that was honestly kind of wild. They said, okay, what if we're doing this all wrong? What if the model didn't have to read word by word? What if it could just look at the entire sentence all at once? And boom, this was their answer. This quote right from the paper says it all. They proposed this new simple network architecture, the transformer. And the key phrase here is dispensing with recurrence and convolutions entirely. They are basically saying we're throwing out that whole one word at a time thing. Instead, they were going all in on this one mechanism, attention.
So, okay, the big question is, how on earth does that even work? How can a computer look at a whole mess of words at the same time and make any sense of it? Let's pop the hood and see what's going on inside. Okay, here it is, the actual blueprint from the paper. Now I know, it looks super intimidating, like a crazy circuit diagram, right? But stick with me, because the core idea is actually really elegant. You've got two main parts. The encoder on the left, its job is to read and understand the sentence you give it. Think of it as the reader. Then you have the decoder on the right, and its job is to produce the output, like spitting out a translation. But the real magic, the secret sauce, is what's going on inside each of those stacks.
And that secret sauce is a mechanism called self-attention. This is the absolute heart of the whole thing. Let me give you an example. Imagine the sentence, the robot picked up the ball because it was heavy. Now, what does it refer to? The robot or the ball? You and I know instantly it's the ball. Self-attention is what lets the AI figure that out. For the word it literally looks at every single other word in the sentence and calculates a relevance score to figure out which words are most important for giving it context.
But wait, it gets even cooler. The model doesn't just do this once. That would be too simple. It uses something called multi-head attention. Basically, it runs a bunch of these self-attention processes all at the same time, in parallel. It's like looking at the sentence from a bunch of different angles simultaneously.
The paper used 8 of these attention heads. And you can think of it like this. It's like having a team of 8 different experts all looking at the same sentence. One expert is a grammar specialist, just looking at verbs and nouns. Another is a storyteller, trying to figure out who did what to whom. A third is just looking for the general topic. And then, the model takes the reports from all 8 experts and combines them. The result? A super rich, multi-layered understanding of the text. And it gets all of this in an instant. Okay, hold on. You're probably thinking, this doesn't make any sense. If it's not reading the words in order, how does it know where anything is? I mean, the cat sat on the mat is a very different thing from the mat sat on the cat, right? Word order is like everything in language. So, what's the trick?
The solution is it's so clever. It's called positional encoding. Before the model does anything else, it injects a tiny piece of information into each word that basically acts like a GPS coordinate.
It's a unique signal that says, hey, I'm word number 1, I'm word number 2, and so on. It's a super elegant hack that gives the model all the word order information it needs without ever having to read sequentially.
So this whole architecture was a really cool idea on paper, but did it actually work? Oh yeah, the results weren't just good, they were absolutely groundbreaking.
Just take a look at this. They tested it on a really tough machine translation benchmark, English to German. The score they use is called a BLEU score. All you need to know is higher is better. And the transformer, well, you can see it there in bold. It didn't just squeak by the old models. It completely demolished the competition.
It jumped the score by more than 2 full points. Now, 2 points might not sound like much, but let me put that in perspective. In this field, that is a huge deal. It's not like winning a race by a fraction of a second. It's like lapping the entire field. It was a massive leap forward.
And if that wasn't enough, here's the real kicker. It got these incredible record-smashing results while being way more efficient to train. It needed just a fraction of the computing power of the older models. So it was better, it was faster, and it was cheaper to run. I mean, that's the holy grail, right? You just don't see that happen very often.
So, as you can imagine, the impact of this paper wasn't just about making better translators. No way. It blew the doors wide open for what was possible with AI and language. It was a whole new blueprint.
So let's just quickly recap why this was such a total revolution. First, parallel processing. That's the big one. Because it could look at everything at once, you could train it on absolutely massive amounts of data, like firehose the entire internet at it massive. That was completely unthinkable before. And second, it finally cracked that long-term memory problem. Because every word can talk to every other word directly, it has no problem connecting an idea at the start of a document to one at the very end.
And those two things, massive parallel training and a long-term memory, that's what unlocked the scale of AI we see today. This architecture, the transformer, it's the literal blueprint for pretty much every single large language model you use now. You know, the T in ChatGPT? Yeah, that T stands for transformer. That's its legacy.
So by tossing out the old playbook and just betting everything on this one elegant idea, attention, this paper completely rewrote the rules. It's an amazing reminder that sometimes the biggest leaps forward come from a single, simple shift in thinking. And it just makes you wonder, right? What's the next big idea out there that's going to change everything all over again?